Welcome all. Today's topic is essential physics needed for us. Physics is headache for somebody, but it is quite interesting for others. Physics has a lot of laws, and we need to know that application in many other places. Coming to the states of matter, we very well know that all the particles exist in three phases: solid, liquid, and gas. The relation between these states is determined by the temperature. In solid, the molecules are bound together very tightly. They can retain the shape. But in liquids, the molecules are bound less tightly so that they can flow. Still, they can take the shape of the container. Say like water, if you pour the water in the glass or a jug, it takes up the shape of the container. Coming to the gas, molecules are still bound loosely. They can also flow, but they do not take the shape of the container. Evaporation. Evaporation is a state where molecules from liquid state escape to the space above the liquid level. When the temperature goes on increasing, more number of molecules enter the gaseous phase, while less number of molecules return back to the liquid state. When the temperature reaches the boiling point, all the molecules enter the space above the liquid. So the state is called gas. But the same gas, when they are pressurized, they can condense back to the liquid state. When the pressure is increased, more and more molecules return to the liquid phase. So the what of the gas becomes liquid again. And it is proportional to the pressure applied. Where these laws get their application? They have a lot of components: cylinder storage, assessment of content, flow and resistance, then finally diffusion, partial pressure, and dissolving. So first we will go for the cylinder storage and content. Basic laws. The Charles law. Charles law says that the pressure is directly proportional to the temperature when the volume is kept constant. If you take the pressure cooker, the volume is kept constant. If you increase the temperature, the pressure goes on increasing. Then coming to the Gay-Lewis law, it says that volume is direct allowed to be kept constant. Volume. The third law is it says pressure is inversely proportional to the volume and temperature is kept. Take a syringe. The piston volume save பண்ணீங்களா? 1 minute அது record ஆகுது. Now coming to the concept of critical temperature and critical pressure. Critical temperature is the temperature above which the gas will be compressed, whatever be the high pressure above. We know it will get liquefied, but beyond a particular temperature, liquefied. What about the critical pressure? It is the pressure required to compress the gas into the liquid status at its critical temperature. If you take oxygen, it remains gas at a normal temperature. If you compress it to the 150 bar centimeter square, like in the cylinder, it will not be. But when you take nitrous oxide and carbon dioxide cylinders, they are compressed at 50 kg per square centimeter. But they compress liquid. So the cylinder contains both liquid and the gas, while the oxygen remains as a gas. Why? Why? Because the critical temperature of oxygen is very low. So that is why if you want to liquefy, you have to reduce the temperature below its critical temperature. Then only it can be liquefied. It is liquefied in liquid oxygen tank, and the temperature is maintained below its critical temperature. So the critical temperature of oxygen is minus 1 Celsius. So you have to take the gas below this level, then only you can liquefy the oxygen gas. But nitrous oxide, carbon dioxide, they have the critical temperature near to the atmospheric temperature, like 36.37 or 31.04 degrees Celsius. So if we apply the critical pressure or the high pressure, they get liquefied even at the level of 50 kg per square centimeter. Now, the physics helps us to understand or measure the content of cylinder. We already know that oxygen remains as a gas because its critical temperature is too low. And drops decreasing, and it is proportional to the reduction in the pressure. If we say 150, and if the pressure is say 75, the cylinder is off. If it is 37, it is quarter. But it is not the case in the case of nitrous. The pressure will not reflect the content. The liquid will continue to evaporate and maintain the pressure. Pressure drops rapidly only when the liquid is not enough to maintain pressure. Look at the last part. We have a zero liquid. So all the gases have evaporated. Now the pressure drop occurs. Because of this problem, then how can we measure the content of the nitrous oxide? So that is measured by the Avogadro number. Avogadro numbers, the thesis says that one molecule give 22.4 liters. See, we have the empty cylinder weight, that is called carry weight. Then subtract it, multiply by 22.4, divide by weight. For example, if the cylinder is measuring 3.4 kg, then we get 730 liters of nitrous oxide. The problem with cylinder storage. We have a cylinder called Internox cylinder where the nitrous oxide in equal ratio. When the temperature is minus 118, nitrous oxide is 36.37. But when you mix oxygen and nitrous oxide in the equal ratio, in the Internox mixture has a critical temperature of 36.5 degrees Celsius. Then stored in walls. The initial delivery is predominantly oxygen. Then after exhausting oxygen, nitrous oxide slowly evaporates, and the predominant gas in the latter half is nitrous oxide. Thus, it will deliver a hypoxic mixture delivery. And we should warm the cylinder to avoid the pointing effect. Coming to the flow, resistance, and venturi. Flow through the orifice. Now we want to know what is tube and what is a orifice. It's more than the diameter. We call that as a tube. When the diameter is more than the length of the tube, We call it the flow through the orifice. In a tube, we have two types of flow: laminar flow till a critical velocity. After that, it becomes given by the Reynolds number. When the Reynolds number is above, say, 2000, the flow will become turbulent. When it comes to the orifice, the laminar distance is decided by the viscosity, and it is given by the Hagen-Poiseuille's law. In case of density, the turbulent flow is affected by the density of the flowing gas. If you take air, its density is 1, 100% oxygen, it is 1.01. Mixture, and there is upper airway obstruction, or even 100% oxygen cannot flow well. While a low density gas like a helium or oxygen, helium has a density of 0.31, can easily flow through the orifice. That is, in the case of turbulent flow, a low density gas will be better. Then coming to Poiseuille's law, here it says that flow is directly proportional to the fourth power of radius to the pressure difference. It is inversely proportional to the length of the tube and viscosity. How to imagine a child drinking a juice. Consider apple juice and lemonade. The apple juice will have a low flow compared to a clear normal straw versus white straw. The child will be able to drink juice easily with a white straw. So diameter, and you take a normal straw and a long straw. Definitely the length of the straw is going. One child will give a high pressure. The flow depends on the pressure applied also. So, affect the flow. If you take the fluid therapy and the blood, so the saline will flow easily because of less viscosity. Blood will 16, 18, 20, 22. Naturally, this will have a larger flow. Pressure applied. If you apply a pressure bag over the IV fluid, then the flow will be. And if you take a long IV line or connecting tubes, then flow will take more time, flow will be less. And apply this in the airway of the lungs. So we will know that is more important. Flow pressure difference by resistance. Or if you calculate the resistance, pressure difference by the flow. So from the Poiseuille's law, so applying the Poiseuille's law, all the factors will get inverted. So the resistance is to the length and the viscosity inversely proportional to the fourth power of radius. This is more important when you choose, especially in children. Even small error increase the resistance by the power of airway edema or spasm, especially in children when there is a small and there is this respiratory difficulty. ET tube length. In case of children, usually children, we cut the length of the endotracheal to reduce the resistance. Now coming to the resistance. Bernoulli's theorem says that increase in velocity of a fluid decreases the heat of applies only to in-viscid fluid flow. It does not apply to a viscous. The lift of air based on this. Venturi phenomenon is an extension of Bernoulli's. When a fluid passes through a narrow path, the velocity increases, pressure decreases. So, because if you have some other tube, so this reduction in pressure will entrain or fluid or gas, whatever is available, into the circuit. This entrainment, Venturi principle and entrainment, is used in saloon, say water. Bunsen burner here, right, to have the flame. Then also when the gas flows through the inner tube, it collapses the bag. So in all these areas, the Venturi. So conventional they have free access to the atmospheric air. So the inspired oxygen concentration will go on varying. In Venturi mass, it is high flow mass. Inside inspired oxygen concentration. That is why these are called Venturi masks. But they require very high flows to FiO2. This is a particular example of various colors and various FiO2 oxygen percentage 28, 35, 40, 60 flow rate settings needed. Where this is important? In case of SPD or with obstruction, they have a chronic hypercapnia. Carbon dioxide accumulation is there. So the carbon dioxide drive is very much, and they have baseline elevated carbon dioxide levels. If we give a high FiO2 and oxygen, they will go for respiratory depression. For carbon dioxide drive, only hypoxia drive keeps them breathing well. If you give excess oxygen, this hypoxic drive will get suppressed. So there will be respiratory depression. Next is Coyanda effect. Coyanda effect is Venturi phenomenon induced at low pressures when there is. So the tendency of a fluid to attach to a wall in curved surface, this is called Coyanda effect. This is same as the Venturi effect. Only thing is, because of bifurcation, it tends to cling to one side and the other side will not get the flow. Where this is more important, if you take the supravalvular aortic stenosis, aortics and one brachiocephalic subclavian, all these are. So whenever there is bifurcation or branching and a proximal obstruction, the blood may cling to flow on one side and we may not get equal blood flow. If we come to the lung and if there is a tumor in the bronchi, so there is a narrowing, and if there is a bifurcation after the narrowing, the Coyanda effect occurs and the air flows preferentially towards this Coyanda effect is applied in fluidic ventilators where there are less number of valves. So you see in this diagram, we have a pushes the flow to one direction. There is a low area of bifurcation, Coyanda effect occurs, that decides which place to, which direction it should go. Next, coming to the flow and temperature. Joule-Thomson effect. When gas under pressure and expands suddenly, the temperature falls. That is cooling occurs. This explains the cooling around nitrous oxide cylinder, and we get expansion of the gas. The temperature falls, so it gets cooled. And if gas flow, then we get some ice formation over the cylinder walls. Now and then we have to clear them. And the nitrous oxide flow meter bobbin jumping. If there are impurities which get obstructed in the cylinder wall, it becomes variable and the nitrous flow meter jumping. So these are all effects due to Joule-Thomson effect, temperature dependent. Flow, adiabatic compression and adiabatic expansion. When the gas from the cylinder wall reaches the yoke mouth, gas is the same without time for the heat dissipation. So increases. The application is do not use this increase in temperature may cause combustion. So don't use oil or grease in the cylinders. Adiabatic expansion. Where this happens, when gas fan without time for heat change, the temperature falls. This property is used in cryoprobe. Pressure and diffusion. Dalton's law of partial pressure. It says that the total pressure of a mixture of gases is sum of the partial pressure of each gas. If there are three gases and they have three individual pressures. If you take the air, 20.9, nitrous oxide 78.1, hydrogen 1.05, and altogether they constitute the air. So air is a mixture of multiple gases, and the total is equal to all individual gas partial pressures. Now coming to the diffusion. In diffusion, Ohm's law states that the rate of infusion is inversely proportional to the square root of molecular weight. What does it mean? If you take two molecules, the bigger molecules less. Then pressure effects, Henry's law. Solubility of a gas is proportional to the partial pressure of the gas above the solution. The partial pressure above the solution is high, then more number of molecules into the liquid phase. For nitrogen, this solubility is 0.0016. For oxygen, it is 0.003. For nitrous oxide, 0.048. And a comparison, nitrous oxide is more soluble than oxygen, more soluble than nitrogen. What is the importance? When you give nitrous oxide in general anesthesia, and if there is a cavity, nitrous oxide more because it is dissolved in the blood more, it diffuses and places the air. Expands. So it should not be used in cavity. Or interstitial obstruction, where the nitrous oxide will diffuse and increase the volume. Nitrogen is least soluble, so it diffuses. Coming to the partial pressure, diffusion, and solubility, we know that to be dissolved more to diffuse. We have two solubility coefficients, oil gas coefficient. What is blood gas coefficient? We take alveoli blood. The gas molecules diffuse from the solubility of the gas. If the gas is more soluble like ether, it will immediately dissolve and the partial pressure. If you take nitrogen or some other gases, if the solubility is less, they quickly reach the partial. In other words, blood gas coefficient determines the onset rate. If it is very low, the onset will be quick. And next one, coming to oil gas coefficient. It is the interface between blood and the brain. Nothing but fat. Fat contains oil. So, interface between brain and blood. So, in more in brain than blood, then it will have more potency. When it is more potent, it will make its minimum alveolar concentration at the blood gas coefficient onset and recovery. See, ether has 12, halogen 4, sevoflurane 0.42. Obviously, sevoflurane will have a short, quick onset and good recovery. And see, trilene nowadays not used. It has the highest oil that is a relation under macro oil. 150 is their product. So it means that when the oil gas coefficient is high, so think of nitrous oxide. Nitrous oxide has very high value. There are few things to be mentioned in the nitrous oxide diffusion and solubility. It produces concentrating effect, augmentation of flow, and finally, diffusion hypoxia is nothing but during the recovery, more and more nitrous oxide from dissolved reaches the gaseous and this dilutes the oxygen so that you are a hypoxic mixture. What's the second gas effect? When the nitrous oxide diffuses, the inhalation agent which is added as a secondary to that, its concentration goes on increasing. So what is concentrated? Only thing is frequency of alveoli. We need to know that the alveoli should be kept better. This difficult for or ventilate the alveoli. Two factors are in maintaining the patency. Presence of nitrogen. Nitrogen is soluble, so they remain dummy the alveoli. So, then Laplace law say that the pressure is directly proportional to the surface tension and inversely proportional to the radius of alveoli. If the radius of alveoli is too big, then you need, if the radius of alveoli is small, very small, then you need a lot of pressure to expand it, just like a balloon. A collapsed balloon is very difficult to inflate, while the already distance it. So the law of Laplace is applicable in alveoli, urinary bladder, and heart form. So this is my answers. Discussed the students this basic physics and measurement in Paul Davies and also Miller anesthesia.